Hello everyone, and welcome to course P21. This course deals with secondary grounding for automation. It explores some of the pitfalls and some of the good and bad practices, best practices that we could use in these processes to make sure our welding operations are stable. So to get kicked off, you have to be respective of the conductivity of a ground. A ground has to have a few different properties to it, and one of those properties has to be a good surface. Now, one of the things I like to talk about is applying a ground and where to apply a ground. The best place to apply a ground is in the center of the work. Don't try to put the ground where the weld is. Take the component, find the center, and put the ground in the center. There's more to do. There's more to consider than just what the distance is. There's more to consider than the temperatures in that area. And you never want to put a ground where the actual weld is going to be that close, because you don't want it to be affected, the material to be affected by the temperature. So putting a ground right underneath it is not the greatest idea in the world. Now, ground surface contacts, if you don't have the right amount of pressure or force on them, you could run into a lot of problems with spatter, with arcing on, and arcing is a real serious problem with some of the HSLAs because it creates hard spots. So we have to be respectful of the metallurgy of the product too. So what I'm saying is a good strong contact is important. A simple set of springs or any type of nonsense like that is not good. Use a hold down clamp or something that gives you a consistent temperature and mass, something you can push on really, really hard so there's something behind it. You got to be able to get enough force on it to keep the temperature under control. If you're into resistance welding at all, you know exactly what I mean, because if you're not pressing hard enough, you will get some arcing and you will get some issues with current. So force is important. Now we also have to be aware of excessive ground system activity. If you take a simple DC voltage current and you run it through steel long enough, it will start to get magnetized. As it starts to get magnetized, it starts to have an effect on the arc itself. Now, when you start getting into confined spaces, and you'll see this a lot, once you're into these confined spaces, you'll actually see sometimes it'll look as though there's a deficiency in the weld metal itself, almost like the wire stalled. Be conscious that this is likely a whole bunch of weld metal that's being pushed or sent out of the weld puddle and onto the floor somewhere in the area. If you can see it, there'll be little balls all over the place, little metal balls. And this is a result of the fields that are supposed to be containing the metal while it's being transferred from the tip of the wire to the puddle. And these DC fields, these magnetic fields, are literally ejecting it. And it'll look as though there's a deficiency in material, but in fact, it's just the material's coming out properly. It's not jamming. It's just blowing away as a result of this magnetism. And in confined spaces, it's far more active. There are ways to check your fixtures for magnetism using Gauss meters. Off location onset, like make sure everything's in the right spot. But at the end of the day, if you keep all your current and your voltages running through your fixture will gain magnetism. And don't forget that even if it's a non-magnetic fixture, like if you used aluminum or bronzes, don't forget that even though those don't have magnetism or collect phase, if we will, don't forget that they set off the fields though. So the more confined the arc is, the bigger your problem. Here's a good example. I've just done this as a picture to show what I mean by arc blow. And you'll get the arc will actually come off the side of the wire as opposed to nice and straight like you would think. And as the condition of magnetism grows inside these fixtures, this starts to happen more and more often. A magnetized fixture will change throughout the day. You may find in the morning everything is just fine, and as it runs harder and runs harder and runs harder, you might find that the magnetism starts to collect. And you might get a call saying, we're off location on a few welds. You go over there, your wire is in the right place, everything's fine, but you can look at the part and clearly see that it's off. Now, what most people do, most programmers do at this point, is the programmers will make a little bit of a change to try to compensate for it a little bit and not truly understand what's going on. And then it might go back the other way the next time somebody has to touch something up and the cell's been sitting for 8 hours because there's no magnetism left in it. It's this variation that causes the problem. And don't forget that it's the routing of, and it's supposed to be a predictable routing of your ground that's key here. You can decide whether or not you want to run voltage through your fixture, through cabling. There's all kinds of devices, and I'll show you a couple of them coming up here, but that can help you with these conditions if they start to get too bad. Now, I'm a big fan of using these pucks. I like the way they rock, but I'm a terrible fan of what they actually do when they're just sitting there flat. This was an accumulation of spatter that ended up on top of this puck, and even though I like the puck concept, I like the fact that it rocks. I like the fact that it's a nice bulky chunk of copper, but I don't like the idea that when the end effector comes and picks the parts up and transfers it to somewhere else, it actually used to drop a bit of spatter on top of this and create a gap. Now, we could see these with our FLIR camera. It was putting burns on the parts, and it was actually starting to melt the or imprint the spatter back into the surface of the zinc, because this was a hot rolled. Lots of excessive spatter. Now, this spatter was mostly a result of arc blow. It was just flying out of this one area and off of another weld, and then it would build up. But be cautious of these little spatter balls. These little spatter balls that collect in certain areas, they're dictating and telling you where the magnetism is and where the magnetism problem is, right? And don't forget, ground locations, the quality of the ground, all these things can affect whether or not you're going to get a good ground. And all this weld metal is supposed to be in the weld. Just as a thought, one of the ways you could combat this, if you happen to have that situation where you're building up, is to use something we know as projection groundings. And this particular one on the left is what you normally buy, and the one on the right is the 3-point projection ground. Please don't use the ones that have like a knurled finish on them, especially if you're using hydroform parts or any oil on the parts, because all those little grooves and things do is they get wet, they start to pick up dirt, and they're awful. The flat ones are better. At least the flat ones, you can give them a wipe and they're clean. The other ones, you almost have to take a sander and sand the surface off of them to get them back down to where you think you got some good material. The projection grounds ones on the right, they will combat all that spatter that might fall on them, and they're my recommended type for situations where the spatter can fall, where gravity can have something land on top of it. That's the one you should be using. Here's a good example of it, of the projection ground push forward. And what I like about it, and if you look up here in this area, I'm not sure you can see my cursor very well, but up in this area here, you can see that this is a stamped part, and 3 points of contact will always sit flat. You can see that the points of pressure on all 3 of these points has been consistent. Now, you have to be very cautious of what you use. You can't use spring-loaded, just spring-loaded whatevers. You have to know you have force on a job to suggest that you have a ground. Simply touching it is not enough. You can buy a ground clamp for 20 bucks that has a big heavy spring in on it. You got to have a hand on you to be able to close it. That's a good sound ground clamp. It can actually squeezes on the part very, very tightly. So I'm always into maintainable grounding systems. I always suggest you use some type of deployment. However, I've seen very good jobs. There's a lot of clever tool makers out there who can figure out how to bring down clamps and actually utilize a hold down clamp for a ground. And the closer it is to the middle, the better. Here's a good example of a grounding problem that's really gone wrong. This is actually a hole from a mounting bracket from a feeder on a robot, and it was actually starting to melt and elongate, as you can see. And what it meant that there was actually current coming back from the wire through the feeder and actually going back through the robot. It was the only pathway that was even possible. I was called to this job because they had a hard time keeping this one robot running. And I said, okay, then let's simply change a feeder, examine one, and we'll examine it and figure out what the problem is. And sure enough, this is where we were. We had a grounding problem, and we never really resolved the problem. It was a particular combination, and I see this all the time now that I'm looking for it. But what we ended up doing was insulating the feeder. Now, some companies already have an insulated feeder, like right from the start. They're already insulated, so if it's sitting on a robot, it's already completely insulated from it. But this was purely that this material had got hot as a result of welding current running right through the feeder and through the robot. Right, this plate was mounted directly to a FANUC. You can actually even see a little bit of the yellow paint in a couple of spots where it was up against the FANUC robot. That's it for this part. Thank you very much. This particular topic is very complex. This was simply an overview. You can feel free to contact me if you want to discuss it further or if you've got a bigger challenge you want to start working on. Thank you very much.